All right, then I'll share my slides.
Okay, you have also 15 minutes and
Okay.
Followed by 5 minutes for questions. Okay.
Thank you. Okay. So, hi everyone. My name is Yu Fei. I'm from the quantitative psychology group at KU Leuven, Belgium. So, good afternoon or good evening wherever you are, but greetings from Belgium. And today, I will be presenting my model of a highly sensitive person. This would be a integrative adaptive network model for the mechanism behind a highly sensitive person. And this project is a collaboration with Jan Troysch, the professor at Free University of Amsterdam. So I'd like to thank you, Jan, for your support for this modeling process. All right, so let's start from the definition of a highly sensitive person, because it's apparently a folk concept, right? But if you try to search this term in psychological literature, what you would find is a term called sensory processing sensitivity, the SPS. So a highly sensitive person is someone who score higher on the SPS scale, and which means they have higher sensitivity to environmental stimuli, and they have deeper information processing. They also have stronger emotional reactivity and stronger tendency of behavior inhibition. So these are the 4 characteristics for a highly sensitive person as a behavior level. And as you might notice that these 4 characteristics are interrelate with each other. And in the following model, I would try to demonstrate how they interrelate together. All right. So SPS is a relatively stable trait across one's lifespan. So a stable trait must have its own biological foundation. And the most well-studied foundation of SPS is serotonin, which is a neurotransmitter inhibitor that many of you might be familiar with. So what does serotonin do? It can decrease the dendritic spine density. If you can see the figure on the right, the dendrites, right? And it has some spines on it. And serotonin can also increase our inhibitory control. So the conclusion would be that a lack of serotonin will lead to a certain level of neuronal hyperexcitability. All right, I hope that's more or less makes sense, because serotonin is an inhibitor, and lack of an inhibitor would lead to hyperexcitability. So let's take one step further, even, yeah. So the serotonin transportation protein gene here, it has 2 variants, the short one and the long one. The short one represents more effective serotonin transportation. So we have talking about the behavior level of a highly sensitive person, the neurobiological level, and even the genetic variance level. What I would like to do is merge these 3 levels of traits together. And how can I do this? All right, we do this as a adaptive network model. And here you can see its graphic representation. And the characteristic of the network model, Sophie actually has already mentioned it. So I will start from the biological line here. So let's start from the gene, this node, this state of gene, and a certain type of gene will lead to a certain level of serotonin. So this connection here is an indication of causality. And the arrow is the direction of the causality. And from the serotonin, we have the spine density. Here is a minus sign, indicates this is a negative influence. And all those previous states, they contribute to a certain neuronal hyperexcitability of a certain person. So this is the biological line. And let's move to the behavior line. Also in the pink panel, the base level. So on the behavior line, we have the first node, which is the word state, our external word. And the next is assess the sensory state, which basically means how much you do pay attention to the world around you. And the third node is the sensory representation state, which means the depth of processing. So the more deeper your information processing is, the more sensory representation you have. All right, so this sensory representation state contributes to the emotional reactivity state here. This is the third characteristic of a highly sensitive person. And stronger emotional reactivity leads to a stronger behavior inhibition tendency. And this state has an active impact on the preparation state of action and the executional state of action, which is the behavior inhibition itself. Yeah, this is execution state of action is behavior itself. All right, so this is the base level of my model. And now the question is, how can we combine the biological line and behavioral line together? So here comes to the second, actually the first order of this model. Those states with capital T, TSS, TSRS, what are they? They are the threshold of sensory state and sensory representation state. And the neuronal hyperexcitability, they has a negative impact on the threshold, which basically means if one got higher neuronal hyperexcitability, the threshold of his or her sensory state will be lower. Then this person is more prone to be excited. All right, so we have this arrow to those two thresholds. And on the second level, we have another assumption, which is this capital H stands for the speed factor, how fast the threshold is changing. Our assumption is the sensory state itself influences the speed that the thresholds are changing. All right, so this graphic is basically all of our assumptions on the model. So I tried to run 2 simulations based on this model, and what I did is get all the parameters preset and only manipulate this connection. So it's from the gene to the level of serotonin. For a highly sensitive person, I assume that this person is lack of serotonin, right? And their gene type just indicates a lower transportation efficiency. So this connection weight, it's set to be 0.2. And for a less sensitive person, this connection weight, it's set to be 1. This is the only difference between a highly sensitive person case and a less sensitive person case. And let's see the difference from these two cases. Let's see what we got here. So let's focus on the X5, this unedged neuronal hyperexcitability here, which is the green line. Oh, all right, we can see that for a highly sensitive person case is almost reach 1. And for a less sensitive person case is actually below 0.2. So the manipulation is successful, right? And let's move to the characteristics, the behavior level of a highly sensitive person, which is they are more sensitive to environment. And this should be represented by the SS. That's the dark red line is still very high, right? It's around 0.9. And for the less sensitive person case is around 0.7. And for the depth of processing, we can see here, this is a sensory representation state. So it's still high, above 0.8. And for the less sensitive person case, it's much lower. You can see it here. And then we have emotional reactivity, the orange line here. Is higher than the less sensitive person case. And we also have the behavior level, the behavior inhibition, this light blue line. This also fits our hypothesis. So this is basically my model and simulations of a highly sensitive person. And my conclusion on that is, I think this is just a promising model and more empirical data can be collected to validate this model. And also more scenarios can be explored based on this. Because if you see, if you pay attention to this, this is quite a isolated example. Because the person is not interacting with anybody, and it does not have a interaction with the environment, right? It only has input from word state 1 at the beginning. So it's just worth it to try more scenarios. For example, how a highly sensitive person interact with a less sensitive person. How do people with a different level of sensitivity interact with each other? That's those are all very interesting questions, I would say. Yeah. So thank you for your listening and attention. This is my email. If you had any further question or something you want to discuss with me, you can just email me. All right, thank you.
Thanks. If someone of the audience have a question, please raise your hand. Okay, no questions. Thanks for your presentation.